That looks like an equation in logarithmic form, right? Namely this. What does that become if you write it in exponential form? B to the A equals 1. So I need to know what power do I need to raise B to get 1? And what power do I need to raise B to get 1? That's why that's a 0. Let's change that question only slightly. What's the log base B of B always equal to? Say louder. 1. Because you would ask yourself, what power do you need to raise B to get B? And well, B to the 1 is B, so that should be 1. The next bunch of rules are ones which we haven't seen yet. But let's state them, and then we'll give like an overview of what this packet contains. The log base B of x times y. So here is an extremely useful fact about logarithms, which was more useful like 50 years ago maybe, but it's still really powerful. And I'll tell you why it was more useful 50 years ago. Log base B of x times y is the same thing as the log base B of x plus the log base B of y. If you see multiplication happening inside of a logarithm, you can replace it by addition outside of the logarithm. And let me tell you why that's incredibly useful 50 years ago. So let's suppose that you don't have access to any electronics because it's 50 years ago. Instead, you have access to a slide rule, which can do addition, and that's it. You also have access to 2 lookup tables. One for values for logarithms. The other one is a reverse lookup table for values of logarithms. So you can translate a 2-in-1 logarithm by looking at the right page in this book, which, I don't know, how many people have seen a slide rule at some point in their life? Have you actually used it though? Oh, good. Yeah, it does addition. Have you ever seen a logarithm lookup table? I inherited from my dad, who is a long since retired engineer, a log table, and it's literally a book filled with row after row of values for log, and that's it. So how would you use this? You would say, I want to multiply 5,373 times 2,797, and maybe I'm log it. It's too hard to multiply those numbers together. It takes too much time. So here's what you do. You look up the log value for one. You look at the log value for the other. Now, your slide rule adds them. Now you know that the log of their product should be equal to. So you grab your reverse log lookup table and figure out what number you would need to plug in there to give the log that you need. And you've just completed multiplication of 2 large numbers. So, no one would do that at this point, right? Because you wouldn't need to. You can multiply using a machine that has other techniques available to it. Still powerful. Anyway, that tangent is over. If log turns multiplication into addition, what do you think it turns division into? Subtraction. And I guess the base doesn't matter here, but you better be consistent with your base. Now let's think about exponentiation. So let's think about what x to the y means. It means like take x and multiply it by itself y many times. Log turns that iterated multiplication into iterated addition. What's another word for iterated addition? What's 3 plus 3 plus 3 plus 3 5 times? I said plus. 3 plus 3 plus 3 plus 3 5 times is 15. Why 15? It's 3 times 5. Yeah. So, iterated exponentiation will become iterated addition. Iterated addition is multiplication. So, the log of x to the y is y times the log of x. Cool. So, those are the well, I guess just 3 rules that are the main takeaway for today. But there are 2 others that are important, one of which you've already seen is important, the change of base formula. According to the change of base formula, what is the log base A of x equal to? So you've had to use this a few times in like WebWalk entry, right? If you want to enter in like the log of 7 into WebWalk, how do you enter it? Log base 7 of 5, let's say.
5 divided by.
Perfect. So, right, WebWalk only believes in, I believe, the log base E. So if you want to use some other base, you can by using the following fact. Log base A of x will be the log, your favorite base you want to walk in, of x, divided by log the base you would like to walk in of A. And I think I'm going to take a moment and put those rules up here. So log base b of x times y becomes the log base b of x plus the log base b of y. X divided by y becomes subtraction. Exponentiation becomes multiplication. Log with respect to a base you don't like becomes log with respect to a base you do like, with some division. And maybe I'll emphasize a few things. This A is the same as that A. This X is the same as that X. And this B can be anything you want, as long as it's a valid base for a logarithm. So can't be 1, has to be positive. You can also express any exponentiation in terms of an exponential you would perform. A to the x is the exact same thing as b to the x times the log base b of a. Let's do the same color coding. A to the x is equal to b to the x times log base b of a. And so this is a very powerful fact in calculus, because you'll learn some interesting facts in calculus about, well, e to the x, the natural exponential. This says that if you know things about e to the x and you want to know things about a to the x, just use this formula with b equal to e, Euler's law. So this rule says that there's really only one logarithm. You just have to be willing to divide to get any other logarithm. This rule says there's only one exponentiation. You just need to be willing to multiply by a log inside of the parentheses. Nice. So let's use those rules to do some things. No, I promised you like an overview of what's in the packet. The next thing in the packet is let's use those rules to do some things. These rules will let you evaluate things that you can't directly. So we'll do a few of those. They let you solve equations that you couldn't solve before. We'll do a few of those. They let you translate from any base to a base that you like better. So you can do that as often as you want. There are consequences about graphs of exponential functions and graphs of logarithmic functions that we'll explore. And how many people have already looked at the Canvas homework that was assigned for today? Cool. Like it's the one that involved like a super long expression to multiply together with a bunch of different bases of logs. This last example will make that one seem very sensible. So there's a call for a reason to pay careful attention there. The last thing that we'll do, and that we won't finish, is we'll explore why these log laws are even true. And the argument that we'll use there is interesting and exciting, and we'll do it once or twice. Neato. Shall we begin? I guess we already have. Any questions before we keep on doing stuff? All right. So let's use this to evaluate. Let's evaluate log base 3 of 2 plus log base 3 of 1.5 without using a machine. Of the logarithm laws over there, which one, does one of them look useful? Which one? I guess up here, the first one, if you're looking there, maybe it's the third one. Nice. So the way I stated it is log turns multiplication into addition, but equality goes both ways. It also says that if you have two logs with the same base added together, you can replace it with multiplication inside of a single logarithm. So doing that, this is equal to the logarithm base 3 of 2 times 1.5. What's 2 times 1.5? 3. So this is exactly the same as the log base 3 of 3. Oh, cool. What's the log base 3 of 3? 1. So here's why this is powerful. This has turned an expression that we could not compute directly into something we can compute directly. We could definitely plug this into a calculator. Depending on how precise that calculator is, it might have some rounding errors built in. It might be precise enough that it doesn't even show you the rounding error. But by just thinking about it, we can know that that answer will be 1. So there's a powerful thing that lets you compute things that you couldn't before. It also lets you solve things that you couldn't before. Let's solve this equation. Log base 3 of x plus log base 3 of x plus 8 equals 2. Right now, our solution technique for logarithmic equations is to rewrite them in exponential form. But before we can do that, we need to have only one logarithm up here. We need log base something of something equals something. If we want to rewrite in exponential form, I see 2 logarithms on the right-hand side of that. But could I replace it with just one logarithm? Which of the rules up here looks like it might be useful? First one. I see a log plus a log. I can replace log plus log with a single log with multiplication on the inside. So let's do that. So this will become a single log base 3 of, I'll multiply the things on the inside together. X times x plus 8 equals 2. Oh, neat. Now I see a single equation in log form. And all the variables are inside of the logarithm, so let's rewrite it in exponential form. What does that become in exponential form? Yeah, so the base is 3. It gets squared equals the thing inside of the parentheses, x times x plus 8. Oh, neat. So there's not any log left in that equation. There's the point. These logarithm laws, that you get down to a point where there's a single log in your equation. Once you have a single log in your equation, you can get rid of it by rewriting in exponential form. Does that equation now look easier to solve? In fact, does it just look like an equation that, well, should I keep on talking at all right now? Cool. Then I am going to stall until you tell me what x is. Dot, 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 dot. There is work that I am skipping. Once you have a solution that you're confident in, maybe compare with those around you. Yeah.
X equals -9.
I hear an x equals -9 and x equals 1. People agree? All right. So, in order to check, because there is a subtlety here, this answer is not quite right. And maybe before I state the subtlety, Why is this answer not quite right? Yeah, there's an issue with the negative. So let's, in order to encourage that, one good way of detecting errors is like graphing. Let's look at a graph and see if both of those look like answers. Because the graph will never tell you exactly what the answers are, but you can look at the graph and say, oh, it certainly doesn't look like there are two answers. So let's graph this. Log base 3 of x plus log base 3 of x plus 8. I want to know, when is that equal to 2? All right, so there is a solution. And the other solution is at -9. Oh, wait, what's the issue at -9? Yeah, there isn't one. That number isn't even in the domain. And this is an example of a situation that I tried to harp on early in the semester. Whenever you do algebra, you might accidentally enlarge the domain. So let's see when that happened by thinking about the domain right now. For the log base 3 of x to make sense, what needs to be true? What types of numbers can I see inside of a log? Positive. So for this piece to make sense, x needs to be positive. In order for that piece to make sense, what inequality has to be true? X has to be greater than -8. So x has to be bigger than -8, and x has to be bigger than 0. So really that just means x has to be bigger than 0, right? Both things have to be true. Is -9 bigger than 0? X equals 1 is the only solution. And let's just see where the domain got screwed up. So let's think about plugging -9 in, because that's like the number that we saw. If I want to plug -9 into the expression that I just underlined in pink, would the result be positive or negative? Positive, because it would be a negative times a negative. Oh, so neat. Both things have to be positive here, but here, because a negative times a negative is positive, the domain has gotten bigger. And we can see that again by looking at the graph. Let's look at the graph of log base 3 of x times x plus 8. Neato. Cool. Does the blue graph look pretty similar to the red graph, but with bigger domain? Yep. So that's exactly what's happened here. All right. Let's carry on. Let's think about subtraction. And I think in the interest of going to the things that I actually want to emphasize, let's solve that equation. So again, it's annoying that I see two different logs here. But do I need to see two different logs in this equation? No. How could I rewrite that as a single logarithm? Yeah.
You do log base 2 of x plus 2 x times x plus 1 equals 3.
Not times, because it's subtraction. Divided by x plus 1 equals 3. Whenever you see a log minus log, it can turn into subtraction inside of division inside of the logarithm. All right. Cool. So now there's only a single log there. What should I do next? Yeah. Change it into an exponential. Perfect. The whole point of getting it into a single log is that you can get rid of that single log by rewriting an exponential form. Ooh, and I'm going to do something wrong. What did I do wrong? Do you think that's a pretty easy mistake to accidentally make if you're like doing homework or a test or something? Yeah, so just keep your eye on yourself while you do that. I'm pretty sure if I just let myself relax and go with it, eventually I'd make that mistake, possibly today. So maybe I didn't need to force it like that. All right, neat. What's 2 cubed? Does that equation look easier to solve than the one I started with? That's what progress looks like. All right, what should I do next? Get rid of the denominator by cross-multiplying it, yes. X plus 2 equals 8 times x plus 1, also known as 8x plus 8. The equal sign matters. Cool. What next? Or should I just be quiet and you'll just tell me what x is? Say louder. I hear a 1 over 7. Do I hear a second for 1 over 7? Do I hear a disagreement from 1 over 7?
I'm stupid, sorry.
I hear multiple calls for negative 6 over 7. Should I actually go through? Or do you see exactly what the error was? Okay.
I just forgot to move the 8 into the
Yeah, I guess that would do it. Yeah. But the question stands. I think that agrees with the answer I remember from roughly 1 hour ago. Should we go through and do the walk together, or should I just pause for a second? Is there demand? Cool. Didn't see any hands. So I think I'm going to stall for a moment. Give people time to fill in the details. Yeah, that's feeling good. So, one of the advantages of these logarithm laws is by taking multiple logs and turning them into a single log, you can get rid of the log entirely, rewriting an exponential form, getting hopefully an equation that's easier to solve. Once you have an equation that's easier to solve, then solve it. Let's do this one last time. So I guess if I just use this rule and that rule, maybe this one will come up in this next example. Let's try to solve this equation. 2 times the log base 5 of x plus 1 minus the log base 5 of x minus 1 equals 2. All right. So stare at that for a second. I think this one I may or may not finish depending on demand. What seems like a useful thing to do? Good, let's combine the logs all into one. Cool, so how do I do that? There's only one thing I have to deal with first. It's not just subtraction. There's a 2 there. Yeah.
X plus 1 squared divided by x minus 1.
Yeah. So you've just done in one step what I think I'll split over 2 steps. But yeah, absolutely. Let's take that 2 and use this rule. 2 times a log, I can move that 2 inside of the log as a power. Log base 5, x plus 1, parentheses matter, squared, minus log base 5, x minus 1 equals 2. And as you just said, division becomes subtraction inside of the log. Log base 5 of x plus 1, parentheses squared, over x minus 1 equals 2. And on the one hand, what I just did kind of makes the equation look more complicated, right? Now instead of a 2 multiplied by it's a square, there's still a log, and it's division now. But why is that a useful thing? Yeah, there's only one log in there. Once you get down to an equation with only one log, you can get rid of the log by putting it in exponential form. So you put it in exponential form, you'll get x plus 1 squared over x minus 1 equals what? 25 sounds right. How many people wound up with a 32 instead of a 25? No, okay, yeah. That would have been if you'd like switch the 2 and the 5, right? Neato. Does that look like an equation that's easier to solve? I think so. And maybe let's say things about how one would solve it without doing it. The first thing I see there is Gesundheit, division. So I could cross multiply over. Maybe even FOIL out that numerator. All of a sudden, the most complicated thing you see is an x squared. Okay, that's a quadratic equation. Get everything onto the same side, use the quadratic formula. So that's like just talking through it. Should we do it? Is there a demand to solve this out? Nice. Then I think I won't. Let's see, so if we use the quadratic formula, that'll probably give us like 2 solutions. Let's in advance see if both of those solutions should be valid solutions. Let's do it by looking at a graph. Don't need this anymore, don't need that anymore. 2 times log base 5 of x plus 1 minus log base 5 of x minus 1. I would like to know, when is that equal to 2? How many solutions does it look like this equation will have? 1 or 2? How many times does the line cross the chord? Just the once. I think there will only be one solution. So presumably one of the 2 things from the plus or minus in the quadratic formula will go away. Will not be in the domain. You know. So, point 1 of the day. These rules can be used to simplify expressions involving logs to things that are easier to solve. Nice. Next, let's say some things about what these formulas let us do. And let's start by thinking about the change of base formula for exponentials. Maybe I'll even jump right down to here. Let's express 2 to the x in terms of an exponential with base 3. So let's do the following. 2 to the x is equal to 3 raised to what power? Let's see, of the formulae you see on the board, which one looks useful? Which of those formulas let us change an exponential from one base to another? Yeah. I don't want to work with logarithms and exponentials. Yeah. So 3 to the x, 2 to the x. So it looks like that A is 2, B is 3. So let's just use those. So by the change of base formula, 2 to the x should be the same as 3 to the x times log base 3 of 2. And just in order to get an idea of what this should do to the graph, I'll tell you that log base 3 of 2 is about 0.66. So this is about 3 raised to the x times 0.63. And let's put this into words in terms of graphs. So the graph of 2 to the x is the same as 3 to the x after, let's see, so 2 to the x is the same as 3 to the x, but it looks like the x in this formula has been multiplied by, let's call that about 2/3. What happens to a graph when you multiply the x in the formula by a number? It compresses if that number were bigger than 1. In this case, it will like anti-compress. I guess that's called stretching. After all x values get divided by 0.63 about. All right, so all of the x values will get divided by 0.63. Division by something less than 1 will like stretch a little bit. So let's use that information. Here are two graphs. And I'll tell you for a fact that one of them is 3 to the x, and one of them is 2 to the x. So if I've labeled them right now as A and B, I'll tell you that one of them is 3 to the x, the other one is 2 to the x. Which one's which? So I just found that 2 to the x should be like stretched horizontally a little bit. So A looks like it's the one that's stretched horizontally a little bit. So all exponentials are really the same as long as you're willing to multiply by a logarithm. And in fact, this is exactly what a computer would do whenever you ask it to compute an exponential with a non-standard base. It'll use this rule. Nice. Let's do the same thing with logarithms. So here are the graphs of log base 3 of x and log base 10 of x. Let's decide which one's which by expressing log base 3 in terms of log base 10. Yeah, absolutely. Thank you. All right. So let's express log base 3 of x in terms of log base 10 of x. Do I have a rule on the board that lets me translate from one logarithm base to another? Yeah. Which rule are you looking at? I guess they're not labeled very well. It's the one that involves logs with multiple bases. So I can translate from log base 3 of x to log base 10 of x using this rule. And in fact, this rule should look really familiar. You've been using this an awful lot because you need it to deal with WebWalk, right? WebWalk only lets you enter things in terms of log of x or ln of x. But it won't let you walk in terms of log base 3 of x, so you've had to use this rule a lot. That's true, right? Cool. So log base 3 of x is exactly the same as log base 10 of x, but what do I need to divide by according to that rule? Log base 10 of 3. If I have the log base 3 of x, so a is like 3, and I want to turn it into log base 10, well then I guess this b is just going to be 10. The x is the thing in the parentheses, the thing in the parentheses in the denominator is the base. Cool. So let's think about what that means. So here we see, as a hint, log base 10 of 3 is around 0.48. All right, so let's think about what this does to a graph. What happens to a graph when you divide the function by, well, that's basically a half. Let's round that ball up. There, basically 0.5. What happens to the graph of a function when you divide the values of that function by 0.5? Yeah. It multiplies by 2. So what will that do to xy coordinates? Yeah. It will compress. In fact, it'll do the opposite. It'll stretch it. So, as was pointed out, this is basically 2 times the log base 10 of x. So here's the observation. Log base 3 of x has the same graph as log base 10 of x with all y values doubled, approximately. So, same question. Here are the two graphs. I'll label one of them as A and the other one as B. I'll try to color code a little bit. So based on the sentence written right here, if one of those two things is the log base 10 and the other one is the log base 3, which one is which? Now let's see. So log base 3 should be the one that's had all of its y values doubled. So B will be y equals log base 3 of x. A will be y equals log base 10 of x. So it looks like all of the logarithm graphs will be the same, just stretched vertically by different factors. And you know what? Let's go ahead and even just see it. So let's introduce some parameter c equals 3. Let's let c run from like 1 to 20. In red, I see the log base 10 of x. Let's also graph the log base c of x. All right, does that seem to satisfy? As that parameter c changes, do all these graphs look the same, but compressed or stretched by some factor? Yeah. That's the point that I was trying to get across here. All right, so let's do one last application with this change of base formula. And this will be particularly well motivated to those who have already looked at the Canvas homework assigned for today. Let's try to compute the log base 2 of 3 times the log base 3 of 2. And you'll notice one thing automatically. It looks like there are multiple bases here. There's a base 3 and a base 2, and that's annoying. But all logarithms with various bases are basically the same. There's a way of translating to get to just one base. So let's do that. Let's replace this problem with a problem that only involves one base. What base should we use? Sure. Not the most efficient choice, but the change of base formula says it doesn't matter. Let's see what happens if we do this. And so let's use the change of base formula and see what happens. Log base 2 of 3 times log base 3 of 2. Let's re-express both of those things in terms of stuff involving the log base 10. And let's start with that. What is the log base 2 of 3 according to the change of base formula? Log of 3 over the log of 2. And I'll include the base 10s just for emphasis. Log base 10 of 3 divided by log base 10 of 2. And now let's think about the second piece. So maybe we'll, just for emphasis, maybe add some color coding to this. So the 3 is the thing in the parentheses. The change in base formula says the thing in the parentheses becomes the thing in the parentheses of the new formula. So this 3 becomes that 3. This 2 is the thing in the base. It becomes the thing in the denominator. So let's use that same philosophy for the log base 3 of 2. What is that equal to? Log base 10 of 2 divided by log base 10 of 3. And yeah, like leaving the 10s out is fine because there's a standard convention. And in fact, the change of base formula says that the base doesn't actually matter. Take a look at that. Do you see anything that cancels up there now? Yeah, it looks like it all cancels. Hold on. The log base 10 of 2 cancels with the log base 10 of 2. The log base 10 of 3 cancels with the log base 10 of 3. When you see fractions and like everything in that fraction cancels, what do you wind up with? So this, in fact, is just equal to 1. And so let's see, those of you who looked at the Canvas homework for today, does it now seem more sensible what I'm trying to get you to do? Yeah. Express it all in terms of a single base and see if some stuff cancels. And maybe I'll even do the following to suggest something that might be a little bit more guiding. I said that log base 10 was an inefficient choice. You just saw it wasn't that inefficient. It couldn't have been that inefficient. It was still pretty easy, right? But I've already got like base 3s floating around and base 2s. Let's pick either base 3 or base 2 and see what happens. I guess I'll pick base 2. So also by the change of base formula, log base 2 of 3 times the log base 3 of 2. Well, if I'm perfectly happy with log base 2, I'll leave that piece alone. Log base 2 of 3 times log base 2 of 2 divided by log base 2 of 3. And now let's just stare at that for a second. Do you see a thing that cancels? Oh, yeah, sorry. Do you see a thing that cancels? Yes, that cancels. What's the log base 2 of 2 equal to? Get the same answer. Which, of course, you'd have to. It was the answer. So the last thing I want to do with my remaining 6 minutes or so is I want to give you an idea of where these formulas come from, why they're true. And I obviously don't have enough time to hit all of these. I'll settle for hitting the first one, and we'll explore this first one in detail. So let's try to compute. Let's try to figure out what the log base b of x times y is. And let's remember it should apparently be the log base b of x plus the log base b of y. And here's the plan that I'll give. So here's a very powerful and extremely simple-minded idea that mathematicians use. If there's something that a mathematician is interested in, they might give that thing a name. That's the whole idea. Give the thing you're interested in a name and see what you can do with that. So let's give things names. Apparently I'm interested in the log of x and the log of y, so I'll give them names. What names would you like to give them? What choice you make doesn't matter, but you have to make a choice.
X and Y.
X and Y. Maybe I'll use capital X and capital Y because lower cases have a job already. The previous section shows Jeff and Rhonda. All right, I'll try to draw them as capital to make them look different from the lowercase ones. Neat. So that's not a big idea. All I've done is made up variable names for the things I'm interested in. But here's an observation to make. I see now two equations. Those two equations are in logarithmic form. What can you do with an equation in logarithmic form? Put it in exponential form. Let's see what it becomes. So this first equation, what does it become if you put it in exponential form? Yeah. B to the capital X equals lowercase x. B to the capital Y equals lowercase y. So how many people are already going to use this, using the letters x and y? Yeah, you don't have to. I'm going to stick with it because I just want to emphasize that it doesn't really matter. But if you want in your own notes to not use the same letter because your capitals and lowercases look the same, pick a different letter. Or pick Jeff and Rhonda. So I have now x is equal to something, y is equal to something. The thing I'm really interested in is something involving x times y. So let's multiply together x times y and see what happens. So x is the same thing as b to the power capital X. Y is equal to b to the power capital Y. Oh, do we have any rules that say what happens when you multiply exponentials together? What is that the same as? Nope. I think you probably meant the right thing, but you said times when you meant plus. Oh, wait, let's see what that means. That means x times y is equal to b to the x plus y. Aha, there's an equation in exponential form. What can I do with an equation in exponential form? Let's put it back into log form. And maybe a motivation for why that's a good idea is when we translate it to exponential form because we know how to do algebra with exponentials. But my final answer, I'm interested in things in log form. So let's translate back to log form because I want to know something about a log. So let's put this back in log form. The base is b. Log base b of x times y is equal to x plus y. And I'm not actually interested in capital X and capital Y. I'm interested in what they represent. What is capital X equal to? Log bx. What's y equal to? Capital Y equal to? Cool. So that's log base b of little x plus log b little y. And now let's just put the conclusion. So this is equal to that. Log base b of x times y is equal to log bx plus log by. Cool. And, well, I've got like a minute left. That's clearly not enough time to go through a similar process again. But maybe I'll just go ahead and point out, do you think you can do something pretty similar to do division? Yeah, I think almost verbatim. To figure out what the log base b of x divided by y is. You could do the same thing again to figure out what the log base b of x raised to the y should be. You could do something fairly similar to get the change of base formula for a to the x, and to get the change of base formula for logarithms. Yeah. So, let's see. In the interest of full disclosure, I don't intend to go through the remainder of this particular section tomorrow or anything. And in fact, the ideas that we spent the last 5 minutes of today on are a little bit beyond what I would expect myself to like assess on exams or something. So, your takeaway is you now know what the logarithm rules are and how to use them. Then you have gotten out of today's class what you were supposed to. Nice. So, as people pack up, maybe I'll ask again, how many people were not here last time and so did not pick up their exam? Just 2? All right. If you want to pick it up now, you can, if you have time.